Okay, YouTube, we've been looking at and exploring how to evaluate limits using tables and graphs. In this video, we're going to look at are three specific instances in which limits tend not to exist. And so let's go ahead and start with example 6 over here. What we want to do is on all three of these show that the limit does not exist. What we'll start with is the definition of a limit in the first place. So let's recall something here. We say that the limit of a function, okay, we say that if f of x or our y values become really close to a unique number, we call this L, as x gets really close to c from either side, then we say that the limit of f of x as x approaches c is that limit there. We write it this way. Well, to be clear about this, I just want to say that our graph or our y values have to approach the same limit, okay, from either side of our x value here. And so in terms of some instances where we see that limits don't exist, we're going to see in this first example that our graph or our function approaches two different values from either side of the x value for which we're approaching a limit for. So we say that showing that this limit doesn't exist, we say that the limit as x gets really close to 0 of the absolute value of x over x. And you'll notice that if we were to plug in 0 here, we would definitely just get, undefined, something undefined. So we'd say, making our table of values here, we have x and our function of x. Looks like we're evaluating at 0, and we do observe that it's undefined at 0. But what we'll do is we'll get really close to 0 from either side. And so I suppose that we could say this is negative 0.001. Here we have negative 0.01, and here we have negative 0.1. And going the other way, we have 0.001, 0.01, and then 0.1. So let's go ahead and start by plugging this function into our calculator here and seeing what we end up with for values. So going to y equals here, to get absolute value, we just go to this little yellow thing that says catalog. Nice thing about absolute values, it's alphabetical. And the very first option is absolute value. So we have absolute value of x in parenthesis divided by x. And so I'm going to go to starting my table, of course at x equals 0 because that's the x value for which we're evaluating this limit. And I'm going to go by tenths in terms of step size here. So making our table, what we can see is essentially for all x values, whoops, you know what I didn't do? I didn't start my table at 0. We'll go back and try this again. We can see that all x values to the left, or all y values to the left of x equals 0 end up being negative 1 here. And so we could see that this is negative 1 and that this on the right side, I don't know if you notice here that all of our y values are positive 1, but they stay that way. And so we get 1, 1, 1 from the right and negative 1, negative 1, negative 1 from the left. And so graphically speaking, if we were to make a graph of this, what we see is this graph of the function of x here, or it's the absolute value of x over x, where it's undefined when x equals 0. But as we look at this function, we say as x values are getting really close to 0 from the right, our y values are getting close to 1. And as our x values are getting really close to 0 from the left, our y values are getting really close to negative 1 here. So because they did not approach the same y value from either side, then we say that no limit exists, or what we do write is we often write DNE for does not exist. So a limit cannot exist if our graph does not approach a single y value or the same y value from both sides, okay? So now taking a look at our next example here, you'll notice that I've labeled this unbounded behavior. And so to be unbounded means to go on forever and ever. As we look at the graph of this, we say discussing the existence of this limit here, we have 1 over x squared, where we have this graph right here as x is getting really, really, really close to 0. So again, this would be really easy for us to just go type in 1 divided by x squared. And of course, we want to make a table that would be centered around 0, since that's the x value for which we're evaluating our limit. And we maybe start by going by tenths or something like that. But if I go to now look at my table, we say what are our y values approaching here as x is getting really close to 0 from underneath x or from above x here. So you can see that as we get really, really close, maybe if we go by thousandths here, thousandths, you'll be able to see something here. As I go back to my table, what we're seeing is as I'm getting really close to 0, start at 0, that our y values are growing so large and they don't stop growing here. So again, with the definition of limit, let's remember this. We say that our y values become arbitrarily close to a unique number L. And since what we're doing on this graph here is our y values, as our x values are getting really close to 0 here, our y values are not approaching a number. What they're approaching is infinity. Then we say that this limit here also does not exist. And the reason why we would give this here, I suppose up here we would say approaches different y values from either side of x equals 0. In this case, it was approached two different y values. In this case here, we're going to say that our function doesn't approach a unique number L, since it approaches infinity, So it has to approach a single y value there, and it cannot just diverge to infinity or negative infinity. So for our last existence or non-existence of a limit here, we're going to look at what we call oscillating behavior. And if you've ever heard of like an oscillating fan, these are these fans that kind of go back and forth and back and forth and back and forth. Of course, we say that our sine curves and our cosine curves oscillate. So looking at this particular function, it's kind of a special function, but we would say, excuse me, the sine of 1 over x, you can see that from our graph here, as we get really, really, really close to an x value of 0, what happens is our y values oscillate even faster. As a matter of fact, the closer to 0 we get for an x value, the faster our graph bounces back and forth between 1 and negative 1. It bounces back so so magnificently fast when x is so close to 0 that it's not actually at a single y value, or we can't declare it that way. So we would say this limit does not exist because of oscillating behavior here. But if we were to go plug this in here, we have the sine of 1 divided by x. I'm going to make sure that I'm in radians mode here. So we say mode radians. And if I go graph this, we could or should see here as we get really close to 0 there. If I zoom in, we'll go zoom in, close to 0, 0. The graph just goes crazy. As a matter of fact, this graph's way better than the one your calculator can make because it's oscillating so fast it can't even keep up with graphing that. So again, if we go to our table here, we'll start our table at 0, and I'll go back over to my table, going by really small increments here. Whoops, table is what we want. We can see that it doesn't exist when x equals 0, but from the left side and the right side, we're not clearly getting close to a single y value there. So we say does not exist because our graph oscillates as x approaches 0 here in this case. So the three instances in which we see a graph not having, or sorry, a function not having a limit at a specific x value are that the function approaches different y values from either side. We could see that, I suppose we have the function diverges to infinity or negative infinity in terms of its y values, or there is oscillating behavior as we get really close to an x value there, oscillating behavior. So these are the three instances here where limit d and e does not exist. Cheers.